Hello, I'd like to welcome everybody tonight. We are very lucky to have Shiva here presenting, who came on short notice, so big thanks to him. We do have a speaker lined up for December, so first Monday of December we'll meet back here at 7 p.m. And without any more further ado,
Hello, my name is Shiva. A long, complicated name, but keep it simple. So, this is work that I did while working with Jordan during my as part of my PhD. So, it's a small technical, I think, interesting problem. So, let me leap into it right away. So, many of you may have seen this picture before. It's a picture drawn by Ernst Haeckel from the 1800s, and this was sort of, if you look from top to down, first is a fish, salamander, tortoise, whatever. It was his attempt to show that he proposed this law that ontogeny recapitulates phylogeny, which is, so ontogeny is the developmental history, that is like a time-lapse video of how an embryo grows over time, and phylogeny is the evolutionary history of a species. So, so he proposed this idea that ontogeny recapitulates phylogeny within a Darwinian framework. And what exactly it is it had basically three basic ideas. The last is the most famous part of it, or the one that has been most condemned since. But essentially, the first is that the ontogeny of an individual in the species is a sequence of phenotypes, and the intermediate states are basically retracing of its history, like all the ancestors. And the third is that that there's an increase in fitness as you go along. So just to go back to this picture again, what essentially is, if you look at the last one, which is the human one, the ontogeny, his basic idea is that if you watch, say, a baby develop, you'll see traces of all the inferior species, like all the traces of species that were evolutionarily related in the past. And basically there is the superior species lie higher and higher on the developmental process. And this is the comparison of different from the very inferior species to the superior, like obviously you're setting up humans are the superior species. So these ideas have sort of long been discredited in biology, and Stephen Jay Gould wrote an entire book on this, basically like to throw out some of the bad ideas but to retain some of the key things that if you were to look at how an embryo gets transformed over time, it does provide some clues, very important, crucial clues about the evolutionary history of the species. So, the basic observation that motivated the work that we're going to see here is, irrespective of its biological correctness, when we look at sort of what we call like the computational, when we look at evolutionary algorithms or artificial life work, when we talk about development, I'll explain how this is basically the crux of what is to come, and I'll unpack it as we go along, is that the ontogeny of an individual, that is the series of stages through which something develops, could in fact consist of valid phenotypes. So in Haeckel's sort of thing was, if you see something that looks like a pig embryo in the process of development, it's actually a reflection of what could be a full-blown adult pig or a fish, which is not true, and any similarities between development across species is merely due to they share certain stages, but there's nothing. It's not like a pig and a human is on top or anything like that. So, but in a artificial system, as I argue here, often it is the case that intermediate stages in development are in fact valid phenotypes. And the other parts of Haeckel's claim are basically are largely irrelevant to artificial systems, that there's almost rarely any relationship between the stages through which developmental algorithm goes through and its phylogeny, that is all the ancestors that it had. But the third part is that the ontogenetic states are not ordered by fitness. That is, if you were to look at the developmental process, it's not that there is a trend towards superiority or better. Like the things that are early stages are not necessarily worse than the later stages. And this is crucial to what follows. And basically the claim that I argue here is that the absence of a relationship between the developmental stages and the fitness of a phenotype has consequences for selection in our evolutionary algorithm. So, just to start off, so this is clearly this is grounded in the problem-solving framework so that we can draw some very crisp inferences, and deliberately there's nothing biological here. So, so the basic problem is, you all probably know, is that evolutionary algorithms typically is framed as an optimization or a search problem where there's a space of candidate solutions. You have a performance measure, a fitness function, and the general goal of the algorithm is to find a good solution or something that maximizes that defined performance requirement. And there are various more complicated versions of this, and I'm going to stick to the basic one where there's simply a number associated with every candidate solution, and you want the solution that's associated with the largest number. So the sort of canonical form of the evolutionary algorithm is just a cartoon of it. Consists of a population. There are in the lower so you have sort of genotypes, and in every generation there's a development portion that may or may not exist and produce. These are basically phenotypes or your candidate solutions, and you evaluate them. You judge how good they are, and the size of these circles are just it's scaled with relation to how good the fitness function assesses each of these candidate solutions. And based on the relative fitness, there's a allocation of sort of offspring on the next generation, and there's a sort of variation applied to these in order to produce these. So there is selection and there's variation, and these are typically the ingredients necessary for evolution to occur in a very broad canonical sense. So there's one aspect that I want to emphasize that's important for what is to follow, is that selection is competitive in a very narrow sense, that suppose in this population, and the size of a circle represents how good a particular phenotype is. So this is a very, if you look at this population where there's just one big guy and lots of relatively less fit individuals, this is likely to be rewarded more offspring with a typical like fitness proportionate selection. But even if in a different context, even if this had the same fitness, depending on who else is in the population, this may end up having a far fewer number of offspring. So the absolute fitness in some sense is not sufficient to guess what proportion of offspring this individual will have in the next generation. So in some sense, this is comparative in a very simplistic kind of way. So what I'm focusing here is on what we call developmental EAs. They've been called by a variety of different names. Artificial embryogeny, artificial ontogeny. So I'm just going to stick to just calling them developmental EAs. And it has to do with a particular interpretation of what is involved in this step here, in this overall process. Most algorithms pretty much retain the remaining machinery, but it's really this part that differentiates these algorithms from the others. So the big part of the motivation for these algorithms are in problems where typically in automated design where, say for example, you want to design a robot, a building, or things that have a lot of structure to them, like things that have as opposed to a set of numbers, like a set of parameters, you want to design a large structure. It has been a classic problem of how do you represent them so that you can actually search through the space of possible structures in order to find something that's good, like a robot or a building or such. And a big motivation for this is that it's for developmental, to call it a developmental thing, is that it sort of has the sense of, since we're calling it an evolutionary algorithm, the representation is sort of like a developmental process. And the promise has been that we can make very weak assumptions about what that solution we're looking for would be like or what structure it will have. So to give you a very simple example, so you want to evolve a patterns, you're looking for a pattern that meets certain criteria and something like this. An example of a typical generative or developmental representation is something like a logo turtle where the genome is represented by a set of instructions to build the phenotype. So for example here, we have a representation that has 3 rules. So forward, forward, left. So it's basically forward, forward, left. So in every generation, this genotype is executed, and it's almost like it goes through a series of stages to produce a resultant phenotype. And it's this process that I'm going to refer to as development, or in a sort of attach the biological word to. So to go from the classic view of the genotype-phenotype map, where there is a genome and it's associated with a single phenotype, when you actually fill in the details of how that the phenotype is actually generated, you have something that looks, every genotype is associated with a sequence of stages through which the phenotype is built out of. So it's not just the end result, but everything is associated with a whole process through which the phenotype is built. So this leads to the main problem that I'm going to focus on here is the typical way of thinking about a developmental representation is that you would run the developmental process till no further change occurs to the embryo as in the initial structure that you're applying the sequence of instructions to, or till you define a maximum time limit which you're going to wait for the whole process to get over. And at that point, the resultant structure is then delivered into the evolving population. And it's on these delivered phenotypes on which the evolutionary algorithm is. So the sort of question here is like, what is the theoretical basis for picking this policy? Like, at some sense, like, how do you decide what time you should stop? Or is it just arbitrary? Is there actually a principled way in which we can say that there is an optimal time at which development should stop and basically this process is over? So this is basically the question that I thought to answer, and I'll tie it back to Heckel and all that stuff in a little bit. So the first thing is that I mentioned earlier, every genotype is associated with a sequence of stages. And here I've just shown 2 examples. And if one sets, say, an arbitrary time of, you wait for 5 time units, and then you say, whatever stage the development process is, I'm going to treat that as the final result of development. So the circles represent, think of it as the turtle that I showed you earlier. These represent points where something novel happens, that is, a new structure emerges. And they can be long phases where nothing happens and suddenly a new structure comes up. So if we were to arbitrarily stop it here, like 5 and 5, that is 5 here and 5 here, for this genotype it would be Phi1, and for this one it would be Phi1 and stuff. Now if we arbitrarily cut it off here, it would be Phi1 and Phi3. If we cut it off here, it would be again Phi2 and Phi3. And if we wait for 20 and we cut it off here, we basically would have the same. So depending on how you pick the point at which to cut and say this is it, I'm just going to wait for this much time, I'm going to treat this as the end product of development, you can get very different outcomes associated with every genotype. So if you think of all possible, if you treat these as all possible ways in which you can, at all possible time points at which you can stop development for every possible genotype, you have a whole space of options. So here the examples that I showed you, 5, 5, 7, 15, they are basically just 4 of a very large, almost infinite number of options that you have available. That is, for one genotype, you could stop it at, say, 3, and for the other, you could stop it at 12, or otherwise you could stop this one at 16, and you could end this at 7. So we have an infinite possible number of ways, time points at which these the development process can be arbitrarily stopped. So, and depending on how we make a choice, each genotype is now associated with a very different phenotype, and it's going to affect how evolution proceeds in possibly arbitrary ways. So here is the question: is how should, say, the genotype had a little homunculus that could point and say, this is it, this is the point, that this is the phenotype that I want to enter into the population because this would maximize the number of offspring that I get. Which one should it be? So this is just a sort of a framework to answer that question of what is the optimal stopping time. So just shown a cartoon here where these are all the possible options available, and there's some sort of decision you have to make to pick one of these and say, this is the phenotype associated with the genotype that should be in the population. So I mentioned earlier that the fitness since each of these are potentially valid phenotypes, they each have in principle, a fitness value associated with them. So the choice of which one enters the population is crucial for more reasons than one. So here is just a sort of illustrative example. Here is the sort of time and the sequence of phenotypes associated with this sequence of this developmental sequence. You have, and this is the fitness associated with each of them. So it goes up and it goes down. It's not linear, does not strictly increase. And this is for the other competing genotype. So if we set an arbitrary limit for both of them and say we're just going to wait for 8 time steps, and the fitness is going to be associated with the phenotype at the end, the O dash, that is the bold line, is going to look a lot better in the final population than the other genotype that is associated with O. But if we pick the red arrows, that is for O we pick this time point 6, and for the bold one O dash we pick 2. The O is going to look much better, have a much higher fitness than O dash. And if we instead pick 4 for O dash and 2 for O, O looks much better than this. So depending on how each genotype optimally picks which phenotype gets in, one could look better or worse than the other. And so if we frame it like a game, so when I mentioned earlier that selection is competitive, in the absence of additional information that is about what the end goal is, and we simply take it as a selfish, that every genotype just wants to maximize the number of offspring, we have no other basis to decide what should look better or worse. Then we can frame this as a game where essentially you have 2 genotypes that are competing against each other, and each of them has several strategies available to them. This genotype has a sequence of strategies. It can pick 1, 2, 3, 4, or up to 8, and the other one has a set of strategies available to it and pick 1 to 8. So if this one picks 2 and this one picks 4, 2 wins. So look here, this one picks 2 and this one picks 4, then this one looks much better. And if this one picks 6 and this one picks 2, this one is looking much better than this one. So if you think of this as a game, and it's not a game of full information where every individual knows what strategy every other individual has. It's basically this one can observe what possible fitness values it has, and it wants to pick a reliable one that will, no matter who the competitor is, it will put its best foot forward in some sense. And there's no one that can beat it if in principle just by virtue of its decision. So in this sense, this is basically equivalent to the optimal strategy for each genome is equivalent to a Nash equilibrium. That is, it is the optimal way for every genotype is to simply pick the highest fitness phenotype, because if it picks anything lower than that, it's possible that some other competitor that may appear in the population that is actually worse on every other way, but it's simply picking a better phenotype. So in order to avoid the possibility that genotype is selected out of a population merely by virtue of picking the wrong one, it is an optimal solution concept for the genotype to pick the highest fitness phenotype. And if all the phenotypes, all the genotypes do that, this is sort of equivalent to a Nash equilibrium for a very large multiplayer. So what does this all have to do in the end? Like when we look at evolution, what implications does it have? So if the genotype phenotype map is not a Nash equilibrium, that is, every genotype is not picking the highest phenotype in its developmental process, then if it's picking something suboptimal, then it's likely that it's generating a phenotype that's good, but it's being prematurely lost because it's simply not being given the fitness for generating that. And I'll show you a concrete example of what this is. And if you look again at this one, this whole thing depends on what the fitness function is. For the same representation in every other respect, if we change the fitness function, these two curves could look drastically different. So which stage is the optimal delivery point is dependent on the specific fitness function that's being used. And if it's not known, then it presents a problem of how to assess which is the best phenotype to pick to enter into the population. I'm just going to give you an example. So the graphics seem to be messed up here, but this is essentially a 10 by 10 grid. Not sure, but these are essentially black squares and these are white squares. And this experiment is to demonstrate or test how important this choice of delivery point in a very practical, commonly used algorithm, the implications it can have. So these are two very arbitrary patterns that I generated just randomly, and the fitness function is, the goal is to evolve a pattern that can cover the black squares and avoid the white ones. And for any given pattern, there are 10 points for covering the black square and minus 10 points for covering the white square. So there's both a bonus and a penalty for evolving this desired pattern. And so, and to do this, I'm going to use the logo turtle example that I showed you. Every genome consists of a simple program that is a turtle that's on the grid, and it has defined a series of instructions: move forward, take a right, take a left, or move backward. And just by tracing out those movements, you get a pattern. We want to use that language to evolve the pattern. And so this is an example of a randomly generated trajectory for this first pattern. And the crucial thing tied back to the second slide is that the fitness can go up and go down. There's nothing that says that as development proceeds, just because it looks more and more complicated, it may have nothing to do with how fit the actual individual is. So this is an actual thing where the fitness of the last phenotype is actually considerably worse than the most simpler starting point. And it goes up and down and it fluctuates, and there's nothing linear or monotonic about it. So this is just the details of the algorithm. Essentially, there are a series of programs, and there are local programs, and essentially we have three variation operators. One is to randomly flip any one of the instructions. The other is to basically cut or add a sequence of random commands at the end. The other is crossover, where you cut a set of commands and you paste it on the other individual. So these are essentially a replication of Hornby et al.'s work, and he demonstrated that this is actually a very poorly performing algorithm. And that is when you use the last, when you just run the program, you wait for a certain amount of time and you pick the last one as being the phenotype. And this uses fitness proportionate selection. So the main manipulation here is that we're going to measure two things. First is to pick the last phenotype. We're just going to arbitrarily pick the last phenotype and evaluate it. And the other is to use the Nash strategy, that is to evaluate the fitness of all the phenotypes and pick the best one. So this is the sort of the main prediction. Is this is the this line here is what every point here is the maximum fitness of the population at this generation, and this is how it changes over time. When you just pick the last phenotype, every genotype is just returning the last phenotype that it produces at some time. And this bold line represents is if we were to evaluate all the individuals and we were to keep track of what was the maximum fitness phenotype, here you'll notice that actually over this entire duration, high fitness phenotypes are continually being generated but lost because they are not being, they're not occurring at the delivery point. And it seems like evolution is just lagging behind the capability of development to continually generate high fitness phenotypes. So this little gap may look very small and insignificant, and why should we worry about this little difference here? Now, the next graph I'm going to show you is, suppose we have a algorithm that's operating with the Nash strategy. This small difference can explode into a very large difference in how the evolutionary algorithm, the dynamics of the evolution actually persists. And so this is the fitness in generating for the first randomly generated pattern. And this is what it looks like for the standard way of using developmental algorithms, where you simply run it for a while and you pick the last one. And this is what it looks like for picking the best phenotype that was generated. And you can see that these bars indicate that this is not the standard error, but it's the maximum and minimum. So it's a lot more liberal than the standard error. So this is for pattern 1 and this is for pattern 2. And you can see that what was a tiny little difference here actually gets magnified into a very large difference in how evolution over a large number of generations, they can lead to a very large divergence in how the population evolve. So here is a graph indicating how frequently does the last phenotype have a lower fitness than some other phenotype on the entire sequence of stages that it goes through. So this is the percent of all phenotypes of all possible pairs. What fraction of pairs are actually better than the final phenotype? So it's normalized because the number of stages vary from individual to individual, and they tend to be almost like 17-18%, and it kind of drops off. But it never quite gets to zero. So, but over time, basically, the last final phenotype does tend to seem to be the most highest fitness, tend to have the highest fitness. But if you look at the Nash map, where it's arbitrarily picking the best one, which could lie at the could be the third stage, it could be the 200th stage. It makes no distinction between first class, it's just between the best one. This could be, it's almost like, it almost never asymptotes to zero or close to zero. It's almost never the case when you pick the best one that the last one turns out to be the best phenotype. Because there is that constraint that selection always should be for the last one is completely removed. So in some sense the ability of a genotype to produce some high fitness phenotype irrespective of its position is as opposed to produce a high fitness phenotype at the last stage. So that difference greatly changes the selection pressure acting on the gene. So to summarize the argument so far is that there's a very simple and straightforward way in which the relationship of how the details of how development, the stages through which it goes through, can directly produce a selection bias. And I showed you here that this is persistently present when you pick the last one. High fitness phenotypes are continually produced, but it's almost like they're invisible, they can't be seen by the evolutionary process. They're there, but they're never considered. And if we were to assume that the genotypes were picking the optimal, this can magnify into a very large difference in performance. So, yeah, I was coming to that. So, first is that in principle there exists a bias. It's continually present depending on the fitness function. And the key point to note here is it's independent of the genetic representation. As long as there is a development stage, whether it's a set of rules, whether it's encoded in a tree or any other form, if it has, ultimately it comes down to a sequence of stages where every intermediate is a valid phenotype. In principle, this bias could be operated. So it really does not have to do with evolvability in a very classic sense of how do you get a genetic data structure that can produce complicated phenotypes. It's independent of the actual genetic representation or the variation operator. So this whole this selection bias is dependent or occurs only if simply growth is unrelated fitness function. That is, the more you grow, the fitter you get. If that rule is not satisfied, then you would expect that this bias would show up in some way. And there's no reason to believe that any fitness function that you have should always be monotonically increasing. That is, the more complicated something gets, the better it is. There's no reason to believe that this should always be the case. And in contrast to the Baldwin effect, where if you assume that there is learning occurring, there is what I've talked about so far is actually, say, you're building a robot, but then it actually has behavior and can learn, then its fitness could have a boost depending on its ability to learn. So the Baldwin effect basically says that if learning can produce a boost, then basically it expedites adaptation. But here, there is a potential for each genotype to have a higher fitness, but it's hidden from selection. So in some sense, there's a retardation of the potential speed of evolution. So in some sense, this is almost like a retarding effect, even though they're somewhat related to each other. So what does this all mean in a practical sense? So the Nash strategy that is to pick the maximum was a theoretical construct that is, in theory, this is the best thing to do. Now, if you were to think of the practical thing that is of evaluating every phenotype, then it's clearly going to involve a far number of more fitness evaluations. So this is where you just pick the last one, and this is the number of fitness evaluations involved. And this is the number of fitness evaluations that are involved in the Nash strategy. So there is a very large trade-off between the cost of evaluating the fitness and the improvement in the candidate solutions that result as a result. But the more interesting issue here is that evaluating, so far, I showed you this picture where it's a little box. We have this little homunculus that can see all the options and can pick the best one. That is basically untrue when we look at this stage process. So the development process cannot be rewound. That is, you can't run through the whole thing and say, oops, I wanted the stage that appeared like 50 time steps, and just undo everything and go back to it. So in some sense, a decision has to be reached based on the current state. And the best example is this reduces the problem to what is we call the secretary problem. That is you are, say, an employer, and you want to hire a secretary, and there are 100 candidates outside, and you want to pick the best one. So each one comes in one at a time, and you interview them, and at the end of the interview, you have to make a decision to either hire them or say no. But the instant they leave, you can't call them back. So how do you, what policy should you use to pick, to ensure that you end up with the best secretary? Because if you pick too early, you haven't waited long enough. If you wait too long, the best secretary may have already gone. So this is a very non-trivial problem of how do you wait. And there are other versions. It's called the picky suitor problem. That is, someone is dating X number of people. The moment you say no, they leave, and you can't. Or the Sultan's dowry problem. Mathematicians like to give these names, but this problem that I described is essentially an instance of that problem, that you can't in a computer, like artificial problem-solving environment, you can do whatever. There are no constraints. But if you were to apply more strict constraints in order to keep with the sort of biological inspiration of this would be, depending on the fitness function, this would be very, very non-trivial to achieve. To produce a Nash fitness genotype-phenotype map, when you have to make a decision and you can't go back, you can't go forward, irrespective of the number of evaluations projected. So this is essentially the ideal delivery problem that tries to Haeckel's thing. That even if there's a slight deviation from that rule that fitness increases with complexity, essentially all kinds of other problems crop up that makes complexity does not necessarily mean evolutionarily adaptive, or there's some sort of global optimal criterion. So yeah, that's about it. Any questions?
Seems like you could, instead of searching the whole space, it seems like there'd be a likelihood that the subsequent creature, which would possibly be somewhat improved, would have an overall depth of search, so to speak, reasonably close to the previous one. So in other words, instead of completely searching the whole space each time, couldn't you record in effect where that species was optimum and let it search within a small window on the assumption that it would sort of evolve from that point? Just as a sort of algorithmic simplification that would get you away from having to, as you point out, search out this enormous space.
So that immediately links it to what variation operators we're using. So here, so one of them was simply mutation, that is at some intermediate point you flip a command, even though it's one small flip. So imagine it's forward, forward, right, left, back, back, back. If you flip one, the resulting structure could almost look nothing like the original. So depending on the variation operator, it does not provide a predictor of what will be or where things will be.
But it seems like you might be able to develop some computational strategies that would gain you quite a few of the benefits without accepting all of the computational costs, which become very significant.
Yeah. Yes. I mean, I'm sure there are many ways, like simple memory strategies or sampling to get you a lot of the benefits. But what is sort of what's compelling about this problem, it almost seems trivial in some level if you do not consider this time constraint. We assume that you can simply sample everything, you can store the fitness values in memory, and pick the best one, and really it's selection among fitness values. But if the objective is to pick the best phenotype, and you're not allowed to arbitrarily go back forward, then it becomes very difficult as well. You only see one state and you have to make a chart.
It seems to me that it depends primarily on the ratio of computation time spent on developing a phenotype versus evaluating the fitness of the phenotype.
Yes.
Development takes a long time, then you can afford to evaluate all the phenotypes, but in fact, evaluation of the phenotype takes an enormous amount of time.
Yeah.
You cannot afford to do that.
So this is in many ways, if you look at many of the papers, this is sort of the dirty little secret in these kind of algorithms. Very often, this is the most expensive operation. Traditionally, fitness evaluation is treated as the standard, but depending on the problem, this can be more expensive.
A good example of the human evolution takes something like 40 years to figure out whether you are in fact best optimized to procreate. Like 40 years is quite a long time to evaluate fitness.
So there's a chicken and egg problem with the solution. Is moment you add time in as a parameter, that means in principle it has to evaluate potentially every possible point where it could stop. So it's adding a very large, it's almost multiplying the size of the solution space by the number of potential stopping points. You don't think so?
It could be a growth problem. Some representations, you're allowed to evaluate so many times that long genotypes are going to be favored.
Yes.
In fact, it will, for some representations, you will evolve a genotype. You align sort of like recursion. You can evolve a genotype that does random separate. And then that will always get not your feedback, but different evaluation time.
Yeah. No, it is actually the case because you're taking out the selection pressure and the last unit being the one you will evaluate. There is a huge amount of the size of when you evaluate the maximum, the size of the genotypes grows. But the main point here is I'm not proposing this as a this is how people should do stuff. There's a very severe trade-off involved, but the point is that development, the generative representations are often treated as a representation issue, but there is a very strong effect on selection which was not seen obvious. And if you want to do it in a constrained way, it's a very theoretically it's a hard problem. But as far as the actual thing of evaluating or picking the best one, yeah, the bloat is a problem and all this other stuff comes along with it. And this is only locally matched, that is, it's not there's nothing here that says that by doing this you will reach a global best solution faster. It is when you do not know what fitness function you're using, it is locally optimal to not select for a less fit. Yeah, the bloat is pretty large. Sorry? So the bloat here is tied to the turtle, the number of comments. Now, if you pick something that has a constant size, like a CA, like a set of views, the bloat would not be necessarily an issue. The size of view that will increase, but the number of stages through which it develops, that's the bloat. That's really because it could go on after the maximum field that was produced. It could keep going on for a while. Yeah, and I don't see how that problem can be avoided by change with any representation.
So the relationship between those two curves very
I did not vary that. I mean, the sort of main result. So this thing was in Hornby's paper. This was treated as a sort of bad representation to simply have a string of commands is treated. But the main reason for picking this sort of thing was there is a selection component that has little to do with sort of the variation operators or those representation dependent decisions that can affect the rate at which are used in that this was a bad thing if you don't, like the L systems do much better than this one. But here all we've done is change how selection or fitness evaluation is. So depending on the fitness function or the variation operator, this gap could differ. But this, for any fitness function that's not monotonic, this gap in principle can occur or be likely to occur.
I'm sure it does. I was wondering if you had the feeling for how it varies
I mean, the main argument here is any constant like clamp on all, it's going to matter to some extent. But basically, any like it's problem dependent. There's no real basis for saying run it longer or shorter. There's no theoretical grounding to know that 100 is good because of X, Y, Z. It's just for some problems 100 may be good, for another 200 may be good, for another 50 may be good. There's no principal way to pick that.
One more question.
Yeah.
What is an L system?
Sorry?
What's an L system? How's it concept?
So the main difference is that these are the genome is directly consists of these commands. In an L system we have a higher level set of symbols. So you have a symbol that says if it's present in the genome, then it's associated with a set. So you basically compress the whole thing into a series of higher level symbols. It's like a production rule. That is, this is compacted into one gene. So it allows more flexibility to do things for you. Yeah, it's basically like a grammar.
All right, well, a big round of applause. Thanks for coming again on short notice, and also thanks for grabbing the VGA converter. If you haven't signed up for the mailing list yet to receive messages on our announcements, please go to breathon.org and you can sign up with the link there. Otherwise, our next meeting will be the first Monday in December, so hope to see you all there. One last note, I guess we're all on one bill tonight, so be sure to get it shortly, so be sure to figure out